So today I will start the last topic, which is Hopf bifurcation. And you can find this in your textbook, which is 12.4. Okay. You can find a very short section on this topic in 12.4. But my approach will be a little bit different. Okay, my approach will be a little bit different. So this is the Dyn12 Hopf bifurcation. Or sometimes just abbreviated as Hopf bifurcation. If you look up the previous lecture notes, all the bifurcation we talked about so far, there are essentially two cases. Either the number of equilibrium changes, or the stability of the equilibrium changes. The Hopf bifurcation is it's very different. Okay, it's very different. Let me show you an example to see what happened in the so-called Hopf bifurcation, which by the way is a very important topic. Okay, it's a very important topic. So we consider the following system. So this is kind of a complicated looking guy. Okay, there are quite a few parameters here. We have mu, we have omega, we have the k here. So in this example here, let's say omega is some positive parameter. K is another constant. It can be positive, can be negative. The mu is our bifurcation parameter. In other words, we're going to find out what are the different behaviors the system has if I change the mu. Okay, if we change the mu. Um, Looks kind of tricky to study, um, but one can easily linearize this. Okay, one can easily linearize this at the origin. Uh, 0, 0 apparently is one equilibrium, right? 0, 0 is apparently equilibrium. If you can ignore the high order terms here, that'll essentially become the linearized version. Okay, the linearized part. The linearized part. So you can go ahead and say, let's calculate the eigenvalues at the origin. By do the usual step. Okay, by do the usual step, do the linearization. But that's a linearized system. You can calculate Jacobi matrix. Remember how we did that? All right, you can easily do this. But what we found is the eigenvalues at the origin turns out to be this lambda. Okay, obviously will depend on the mu. Okay, turns out lambda mu equal to mu plus or minus I omega. Now omega is a positive parameter. For those who are still wondering why is mu plus or minus I omega, let me just tell you that so-called Jacobi matrix turns out to be just mu, negative omega, omega, and mu. You can go ahead and calculate the eigenvalues here, but that's what it is. So if you look at this eigenvalue at the origin, you can easily tell the eigenvalues are complex numbers. Has a real part, has a complex part. So the origin will be some kind of a spiral. It can be a spiral source or spiral sink, depending on the sign of mu. Okay. If mu is zero, essentially we have a center. Okay, the linearized system has a center at the origin. Turns out, and as mu, if mu goes from some negative number to positive number, like I said, the whole system depends on mu. Okay, the mu is our bifurcation parameter. We want to find out what happened if I change mu. So as mu changes from some negative number to positive number, the origin changes from if mu is negative, has a negative eigenvalue, the origin will be stable. Okay, will be stable. So it'll change from a spiral sink to a spiral source. All right. So that's a preliminary analysis. And let's take a closer look by put this into polar coordinates. We have done converting a system into polar coordinates before. So there are some detailed calculation that I did not carry out here. So you can look up the previous lecture videos and look that up. Polar coordinates, there is this r, which will be a function of t. There is this angle, which is also be a function of t. And we do the time derivative. R turns out to be mu r plus kr cubed. Theta prime turns out to be omega. So I guess theta prime really refers to how the point will be moving. The fact that the omega being positive, meaning theta will always increase. Okay, in other words, the point will always move what? Counterclockwise. So that's that part. So we should be focusing on this single equation here. This one is about r. R prime is mu r plus kr cubed. So this is actually a single variable. This becomes a single equation. R is mu r plus kr cubed. So let's take a look at one scenario. Okay, first, let's find out one case. That is one case negative. Let's analyze this scenario first. If mu is negative, if mu is some negative number, think about the equilibrium to this problem here. If mu is negative, case negative, so give yourself some example. For example, negative r, say minus 2r cubed. Right? You can factor out the r. There is a negative sign in front. It's 1 plus 2r squared. So if you look at this guy here, the r has only y equilibrium. That is r equal to 0. There won't be any r make this part equal to 0. Moreover, r prime it will be a negative sign. So you can find out all trajectories tend to r equal to 0. In other words, r equal to 0 is stable. Okay, r equal to 0 is stable. Keep in mind, okay, now the problem becomes one-dimension problem. So my single statement here, this one, may take some thought, okay? Not everybody understand what's going on here. So I want you guys to think about this. Second scenario is mu equal to 0. Then the equation is just r prime equal to kr cubed, where k right now is assumed to be some negative number, okay? So once again, you can figure out that all trajectories also tend to r equal to 0, but perhaps at a slower rate, okay, at a slower rate. Not that it matters, but just something that we can notice. Let's look at what happens when mu is positive. Now, when mu is positive, mu being a positive number, k being a negative number, so you can factor out, say, mu r. So once again, there are actually two equilibriums. One is r equal to 0. Keep in mind, okay, this ratio here is a negative number. K is negative, mu is positive, so this is a negative number. So I can solve for r, which is square root of mu over k's absolute value. So there are two equilibriums. You can analyze which one is stable, which one is unstable. R equal to 0 turns out to be unstable. Okay, let's call this is repelling. And the other one is the equilibrium that's attracting. So think about why that is the case. Okay, you can sketch the graph of this. I guess you can sketch the graph of this to find out what happened. So let's take another look at this. When mu is less than 0, all trajectories tend to r equal to 0. R equal to 0 really is just the origin, right? Because the radius distance is 0. Mu equal to 0 also tends to 0, so there's not much of a big difference here. But when mu is positive, r equal to 0 is repelling. And this is actually a circle, by the way, all right? Or the radius equal to this actual circle is the equilibrium that's attracting. So I like to plot the graph of this. So compare the nodes with what I'm about to sketch. Okay, mu less than 0. So this is the essentially the r axis. This is the r. All right, r equals 0 is the only equilibrium, and all the trajectories will approach 0. Mu equal to 0. Actually, it's also approaching the origin because it's stable, just slower. And when mu is greater than 0, so this is r, okay, this is the r axis because it's a single equation, okay, it's a single equation. There are two equilibriums. One is r equal to 0, which is unstable, and back here it is that positive r given by this formula here, and this guy is attracting. Unstable, unstable. So this is in the polar coordinates. In terms of the original x and y system, here's actually what happened. Okay, here's the x-axis, y-axis. Here's the x-axis or y-axis. This is the phase portrait. Okay, this is the actual phase portrait. When mu is negative, all the solutions will approach the origin. Moreover, the fact that theta prime is positive, the angle keeps increasing, right? So if you start somewhere on this right here, the angle always increase. Okay, the angle always increase. See the angle? So that was a smaller angle. It's getting bigger and bigger. The angle will increase, but at the same time, the trajectory has to approach what? Has to approach the origin. So it's getting closer and closer to the origin. So this is the spiral. As we said, this is the spiral sink. Okay, spiral sink. The origin spiral sink. This guy is essentially the same case. It's just that approach it is a bit slower, at a slower rate. So it takes a bit longer to get to the origin. So that's why this one is spiraling towards the origin much faster than this one. So you're looking at some bigger circle here, I guess. But essentially the origin behaves the same. This is also a spiral sink. The most interesting part is what happened when mu crosses zero. When mu crosses zero, when mu is something that's even slightly positive, the origin becomes unstable. But then there is this circle. Okay, see, this is actually a circle. This is actually a circle. There is actually a circle with radius given by this being, well, attracting. What does that mean? That means if you start somewhere around here, for example, the trajectory will move away from the origin, and approach this what? And approach this circle. Now becomes periodic, and eventually becomes periodic. From the outside, if r is bigger than this radius, it will also approach what? Approach this circle. Okay, approach this circle here. So this is what we call limit cycle, a periodic solution. Okay, so this is the limit cycle. So let me write down what we observed. So there is this appearance of a limit cycle. Appears when the origin, the origin was stable here and then becomes unstable. Okay, stable here and then unstable. It appears when the origin becomes unstable. And the limit cycle, referring to this closed orbit that we sketched, the limit cycle is it repelling or attracting? Is it repelling or attracting? Okay, so in this case here, the limit cycle is stable. It is attracting. And we call this, so this is called a bifurcation. Okay, Hopf bifurcation. Hopf bifurcation refers to the fact, the appearance of a limit cycle. No limit cycle, no limit cycle, and there is a limit cycle showed up. So this phenomena, this behavior is called a supercritical. Supercritical refers to the fact that limit cycle becomes what? Attracting. Okay, supercritical Hopf bifurcation. Supercritical Hopf bifurcation. In terms of the actual solution, so this is the phase portrait. Okay, in terms of the actual solution, obviously I can plot x and plot y. So here's t-axis. Here's the actual solution of x of t. When mu is negative, all the solution becomes close to zero. So you start somewhere at a higher level, It kind of oscillate, but eventually dies down. Okay, becomes, you know, 0, getting closer and closer to 0. But then, so this is once again, this is for mu negative. When mu is positive, the solution all becomes almost periodic. That's what it means, right? You start somewhere inside, and it becomes almost periodic. Starting outside, in the long run, it approaches periodic solution. So the actual graph of x of t could look like this. If you start with a large amplitude, it'll shake a little bit, but eventually it dies down and becomes almost a periodic solution. Okay, this becomes periodic. All right. If you start with something that's very close to the origin, it'll start shaking and becomes almost periodic. So that's supercritical Hopf bifurcation, and this happens when k is negative. So we can do a very similar process and figure out that when k is positive, we have similar behavior. Mu negative, there is this guy that is unstable. So this is actually periodic solution, okay, in polar coordinates. And mu is 0. The origin is repelling. Mu greater than 0. The origin is also repelling. So I do the same phase line analysis. Mu negative, 2 equilibrium, 0. And this R, this positive R, this guy is unstable. The origin is stable. Mu equal to 0. The origin is what? Unstable. Greater than 0. The origin is also unstable. So in this case here, when mu crosses from positive number to negative number, when mu goes from some positive number to negative number, you will have a periodic solution that shows up, but the limit cycle is what? Repelling. Okay, repelling. Here's the phase portrait. This case here, phase portrait. So there's this rate, this R, X, and Y. There is this circle here that is repelling. It's repelling. So if you start somewhere around here, for example, the trajectory will move closer and closer to 0. Okay, it'll move spiraling towards 0. Okay, spiraling towards 0. And if you start somewhere close to the limit cycle here, it'll spiral away. Okay, it'll spiral away. This is the same. There's no closed orbit. The trajectory simply spiraling away. Okay, and same story for this one. So this is a different story. Okay, so this is a different behavior. The limit cycle appears when the origin becomes stable. Right? Unstable, stable. unstable, stable. You just have to look the other way around. Okay, unstable, stable. And the limit cycle is repelling. This is called a subcritical. So what I just showed you guys is just an example of Hopf bifurcation. Put it simply, Hopf bifurcation is simply the case where the limit cycle occurs. There is a periodic solution coming out of nowhere. That's what we call this Hopf bifurcation. That was just one example. In general, how do we show there is actually Hopf bifurcation? That's a different story, okay? To prove the existence, to prove the existence of Hopf bifurcation is a different story. And that is often the key part of any research. That's often the key part of any research. There is one theorem that I like to write it down, and you guys don't necessarily have to understand this. So for this class, just understand the meaning of Hopf bifurcation. What's the meaning of it, but not prove it. Okay, but not prove it. When you guys some of you will get to graduate school, and hopefully you will learn this again, and then you have to take a detailed look and how do we prove it, or how do we prove it. So this will be the last part of our class, okay, our class, and we put this into a theorem. This is a general theorem on the existence of Hopf bifurcation. Hopf bifurcation. In our previous example, what you notice is when mu goes from negative crosses over to positive, you will have some periodic solution popped up. How about in general? Okay, how about in general? So consider any system, and instead of use x and y, I use a vector form, capital X. So this capital X is going to be x and y, okay? The right side will be obviously a function of x. So once again, capital F is really one function. You have the first equation of the two functions. You have the first equation of the second equation. F depend on mu, because mu is the bifurcation parameter. So this just means a function, okay, that has parameter mu in there. Depends on a parameter mu. So here's how you do the prove the Hopf bifurcation actually occur. Suppose that there is an equilibrium x star that also depend on mu. All right. You're gonna figure out the equilibrium that depend on mu, and then go ahead and calculate its eigenvalue. And we call this lambda. Once again, lambda also depend on mu. That has a real part alpha, that has a complex part I beta. So this is alpha plus or minus I beta. But obviously the real part and complex part, they also depend on parameter mu. So we call this alpha mu and we call this beta mu. Those two terms, okay, they're expressions of mu, okay, they're expressions of mu. For example, alpha mu could be something like square root of 1 minus mu, for example, okay? Assume beta mu is not 0. So this part, the complex part is never 0. The complex part is never 0. I want you to compare this theorem with the previous example I showed you, okay? And alpha mu, now alpha mu in general is not 0, but sometimes can become 0. Sometimes it can become 0. So let's say alpha mu equal to 0 at some point mu naught. So that's like a key point here. If you think about this condition here, alpha equal to 0 is some mu naught, means this real part becomes 0, and that's essentially a center, isn't it? You have a pure imaginary eigenvalues. That's essential center. So that's the key requirement. So you need alpha mu naught to be 0. In this case here, you're going to set this equal to 0. You have your mu naught to be, well, 1, okay, to be 1. You're going to need this to be 0. And that's not enough. If you can further show, alpha mu is a function of mu, right? So you should be able to differentiate it with respect to mu. You should be able to differentiate it with respect to mu. And you gotta evaluate this at mu naught, at that critical point that you found. If this is not 0, okay, if this is not 0, and then you have Hopf bifurcation, and then you have the following conclusion. So that's one requirement. That's the second requirement. Okay, these are the two requirements. This is what you use to find mu naught. This is the condition that you need to verify. Supercritical bifurcation. If this is attracting, okay. In our previous example, this x star at mu naught will be 0, okay, will be the origin. If this is attracting, then there will be a small attracting limit cycle shows up, okay? Around this critical number, okay, for mu minus mu naught small, and mu bigger than mu naught. So when mu crosses over mu naught, when mu crosses over mu naught, you will have an attracting limit cycle. And then we have the subcritical bifurcation. If this is repelling, then there is a small attracting limit cycle when mu is close to mu naught, and on the other side of mu naught, okay, when mu is less than mu naught. All right. So the key, all right. So this is the part that tells you what kind of a Hopf bifurcation it'll be, but this is essentially the most important condition that you need to verify. You're going to use this to figure out what is the mu naught has to be. You're going to verify this derivative with respect to mu being positive. All right. You're going to use this to say there will be Hopf bifurcation. You're going to use this to find out what kind of bifurcation it is. Is it supercritical or subcritical? So try to compare this theorem with the our previous example. Okay. And that'll be the end of this class. And hopefully you guys learn a few things. There are many topics that we simply did not get into the details. That requires a deeper course. maybe you guys hit graduate school, you will learn this again, and hopefully you can spend more time finding out some more applications of this. All right, that's it.